Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 7, Lesson 7, Factoring Special Cases. After this lesson, you'll be able to factor special trinomials, for example, the perfect square trinomial. So like we did in a previous lesson, we were looking for special patterns that we could recognize to factor more efficiently and more quickly. And there is a special pattern that we can look for with trinomials, with quadratic trinomials. For the critique and explain, we have Seth and Bailey, and they're given this original trinomial. It's a quadratic trinomial, and they factored them. Seth got 8x plus 24 times x plus 3, and Bailey got 2x plus 6 and 4x plus 12. Now, neither of them factored completely, right? Because I can still pull out a 3 from that one, and I could still pull out a 2 and a 3 from there. So they didn't factor them completely, but they did both get something that would be equivalent to the original trinomial. They just had different factors. So are there other pairs of binomials that are different but whose products are equal? Well, let's try, 3x plus 3 times x plus 5. What would that give me? It would give me 3x squared plus 15 plus 3 is 18x plus 15. So that would be the trinomial it would give me. And how else could I get that? Well, I could do x plus 1 times 3x plus 15. Would I get the same trinomial? 3x squared, 15 plus 3 is 18x plus 15. So I'd get the same trinomial, but I have different factors, and these are all not factored completely either, but because we could pull out a 3 here and we could pull out a 3 there. So you can see you can get equivalent factors, but if you're not factoring completely, you're going to get two different answers. So let's look for some special patterns to help us factor what's called a perfect square trinomial and the difference of two squares. So remember, difference of two squares was a binomial that we recognized before. So here's our trinomial, x squared plus 14x plus 49. This is called a perfect square trinomial because the first term and the constant, the last term, are both perfect squares. So look at that. X squared, I can break that up into x and x. 49 is 7 squared. So I have two perfect squares. And there's a pattern. If the linear term is positive, it's going to look a lot like a squared plus 2ab plus b squared. We know that pattern, right? It's going to be our binomial squared. And if the linear term is negative, well, then it's just going to be our a minus b squared, or our a squared minus 2ab plus b. Now let's look. What is the second term, or this outside term? It's 7. What is 7 times 2? If I double it, I do get my linear coefficient. So it might be confusing because now we're not thinking of a and b and c, right? Our constant we're not calling c because it's following this binomial squared pattern. But it's the same thing. Our constant, so you take the constant squared, and you take the square root, and then you double it, you'll get the linear term. And the same with the negative. So let's see, if we begin factoring with the last term as a perfect square, we would say, okay, it's 7, and then double 7, and we get 14x. And then that means we have our binomial squared. So we have x plus 7 squared will give us that trinomial. And if we have a negative linear term, it's the same thing, except it's going to be minus 2ab. So let's look at the first term. My first term, is that a perfect square? Yes, 9 is a perfect square, and x is a perfect square. So what we did was we took 3x and we squared it. What about the last term? 25, is that a perfect square? Yes, it's 5 squared. So now we're going to take a times b, so this is a, this is b, and we're going to multiply them together and double it. What do I get? 30x would be my linear term, and that's right, it's just going to be negative. So then we'd have minus 30x. And since we recognize this is a perfect square trinomial, we can say, oh, it's just going to be a minus b squared. And what is a? 3x. What is b? 5. Square it. There's our factored form. So if you can recognize this pattern, then you don't have to go through the steps of regrouping or doing the reverse distributive property. If you just remember this pattern, that it's going to be a binomial squared, you can factor it very easily. So let's try. First, we're going to check, is this a perfect square trinomial? So this is always a good first thing to do. When you get a trinomial to factor, look for the special cases first. So let's see. I recognize 4x squared is a perfect square. It's 2x squared. And I know 9 is a perfect square. It is 3 squared. So there's my A and my B. So I'm going to do A times B and double it to get my linear term. 6x, yep, that gives me positive 12. So now here's my binomial squared. It's just going to be, I'll write it down here. A binomial squared, it's positive because my linear term is positive, so it's going to be my first term, 2x, plus my second term, squared. Don't forget the squared. It won't work if it's not squared. You can check by distributing. Let's do that. Let's check by distributing. So my pattern would be a squared plus 2ab plus b squared, if this is a and this is b, with our binomials. Let's do it. 2x squared would be 4x squared. And 3 squared would be 9. And 2 times AB, so multiply these together. 2x times 3 is 6, times 2 is 12x. It would work. Okay, let's do part B. First, check, is it a perfect square? Yes. I have x squared and I have 4 squared. Double check, if I do x squared times 4, I get, or if I do x times 4, I get 4x, and I double it, I get 8x. So this must be a negative 4x. So this must be a negative 4 squared to give me positive 16 and to give me negative 8. So then I know it's going to follow my binomial squared, and my first term is x, and my second term is negative 4. Application problem, factor to find a dimension. So we're going to look at volume, and if we remember, volume has 3 dimensions, length times width times height. We're working with something cubed. Sasha has a tech store and needs cylindrical containers to package her voice-activated speakers. A packaging company makes 2 different cylindrical containers. Both are 3 inches high, so we know this is 3. We know h is 3. Determine the radius, so we don't know the radius of either. Okay, we don't know the radius. How much greater is the radius of one container than the other? But we do know the volume of each. We do know the volume of each. Notice the volume for the second one is factored. They pulled out a pi. Okay. So the formula for the volume of a cylinder is pi r squared times height, right? Area of the base, which is a circle, so area of a circle is pi r squared times the height. R is the radius, h is the height. The height of both containers is 3, so instead of h, we just substitute the 3. So then we have the volume equals 3 pi r squared. Okay, and so since we know that, and then we know this equals the same, so the volume, 3 pi r squared, is going to equal this. So let's set that up. 3, I'll do that here. The volume is going to equal whatever they told us the volume is. So the 3 pi's are the same, they'll cancel, and r squared is going to equal x squared. That means r is going to equal x, so the radius is going to be x for this one. For the blue speaker, the radius is going to equal x, whatever x is. Okay, so let's look at the second cylinder. 3 pi r squared, that's the formula for volume, is going to equal this number. So if we wrote that out, 3 pi r squared is going to equal whatever that number is. Pi times 3x squared plus 30x plus 75. Squish it in there. Okay, I can cancel out a pi. So then I'm going to have 3r squared is going to equal this thing. 3x squared plus 30x plus 75. I want to factor that, right? I can pull out a 3. So then we'll reverse distribute 3 times x squared plus 10x plus 25. Okay, so all I did was factor, pull out a greatest common factor. Watch what I can do. I can cancel out the 3's. Okay, and now I need to factor inside the parentheses now. So I'm going to have r squared equals, now I'll do by binomials, x and x, 5 and 5. Did we check? We forgot our step. Let's check. Inside the parentheses is a perfect square trinomial, x squared and 25. So it's going to be something squared, one binomial squared, x plus 5. I can take the square root of both sides, so r is going to equal x plus 5 over here. So the radius of the blue cylinder is just x, and the radius of the black cylinder is x plus 5, or it's 5 units or 5 inches more than the radius of the blue cylinder. What is the radius of a cylinder? That is a height of 3 and a volume of that. Okay, so h is 3, so let's remember the volume equals area of the base times height. So if I substitute height of 3, I get 3 pi r squared. That's my formula for volume. So that formula, 3 pi r squared, is going to equal all of that. Pi times 27x squared plus 18x plus 3. The pi's will cancel. Then I'm left with 3r squared equals all of this. I probably need to pull out a greatest common factor. I can pull out a 3. Then I've got 9x squared plus 6x plus 1. I like that. Why do I like that? Because inside the parentheses now I have a perfect square trinomial. So I'm going to cancel out the 3's. I'm going to have r squared equals, this is a perfect squared binomial, so I know it's going to fit the pattern of a binomial squared. A plus b squared. What is a going to be? What's the square root of 9x squared? It's going to be just 3x. And the square root of 1 is 1. Now I'm not done yet. I got to take the square root of both sides. So r is going to equal 3x plus 1. Remember, every time you take a square root of a square, those are opposite operations. They just cancel each other out. Example 2, what is the factored form of x squared minus 9? Do you remember what this is called? This is the difference of two squares. Okay, and we know that this pattern is going to be binomials with opposite signs. So if we factor that, we just need to look for what is squared and put those into our parentheses. So for instance, what is squared here? Well, only x is squared, so that comes here. And then what is squared in my other term? 3 is squared, so that goes there. It's really easy. Okay, factoring, if you can remember the difference of two squares, you can factor them very easily. So our next example, 4x squared minus 81. 4 is a perfect square, so what am I squaring? I'm doing 2 and x. That's what I'm squaring. And 81 is just 9, or negative 9. And so then my first term is going to be 2x, and I'm going to have plus 9. And then my other binomial just has the opposite sign, because remember, it has to have opposite signs so that the linear terms cancel out. In our perfect square difference of two squares, we do not have a linear term. They have to cancel each other out. Okay, let's factor these. Look to check. Does it follow a special case? Yes, it does. This is a difference of two squares, so I'm going to take the first term and split it, and then take the square root of the second term, which is just 8, and I have opposite signs. That's it. Okay, for part B, same thing. You're going to have two binomials with opposite signs. Take the square root of the first term, which is 3x. Take the square root of the second term, which is 10. Example 4, factoring out a common factor. So just like we did with trinomials, sometimes we first have to factor out a greatest common factor, and then we can see the special case. We saw that with the cylinders. We saw that with the speakers. We had a perfect square trinomial once we factored out the 3. So we have 3x cubed y. That's not a perfect square. And negative 12xy cubed, that's not a perfect square. But what if we pull out the 3 and the x and the y? They all have a 3xy. So if we pull that out, what do we have? If we do the reverse distributive property, 3, I need 2 more x's and I don't need my y. And then I need to multiply 3 times negative 4 to get negative 12. I already have my x, so I need 2 more y's. So then we have this special case in our parentheses. We can recognize that's a difference of 2 squares. Okay, and what we're squaring is we are squaring x, and we are squaring 2y. Because 2 squared is 4, y squared is y squared. And then that's what we put inside parentheses. Notice we're always writing our greatest common factor out front. Don't lose it. And we do our binomials with different signs, x plus 2y, x minus 2y, using the different squares pattern. So always a good idea, check for these special cases first. The first step, look for a greatest common factor. Then second step, check for special patterns. Let's do try it number 4. We're going to factor them. First step, look for a greatest common factor. I can pull out a 4 and an x. Okay, I'm always looking, if my first term is not quadratic, I probably can pull out an x. It's probably part of my greatest common factor. So let's pull out a 4 and an x and then rewrite what we have. I would have 2 more x's. I'd have a 6x, and then I would have 9. That is a perfect square trinomial that fits one of my patterns. So I'm going to rewrite my 4x. I'm not going to lose my greatest common factor. And I'm going to remember my perfect square trinomial follows a binomial squared, something squared. It's going to be x plus 3 squared. And you can double check by distributing. If I do x plus 3 squared, it's going to be x squared plus 2ab. 3x times 2 is 6x plus 9. And if I multiply all of that by 4x, I get 4x cubed plus 24x squared plus 36x. That is my original trinomial. Okay, so here's our answer. Part B. Look for greatest common factor, 50 and 32. They're both even, so pull out a 2. I can't pull out a variable. So then I'm going to write what's left, 25x squared and 16y squared. I like that because I have a difference of 2 squares now. I'm going to rewrite my greatest common factor. Difference of 2 squares is just 2 binomials with different signs. Take the square root of the first term. What's the square root of 25x squared? 5 and x. Take the square root of the second term. It's going to be 4 and y. There's our answer. And you can go through and check using the distributive property. You've made it to the concept summary. You've made it all the way through topic 6. Great job. Factoring special cases of polynomials. So again, I'm just going to recommend first step, check for GCF. Step number 2, I would check for patterns or special cases. I'll call it special patterns. And then continue with your factoring. If you have any questions, put them in the comments. Make sure to like and subscribe and come back for topic 8.